Thank you. I'm really happy to be here today and to talk about this topic. So I will talk to you about the Swedish National Timescale, UTC SP, and also about how this is related to the International Timing System. And in order for you to get a grip of this, I will give you a quite thorough introduction, historical perspective, and eventually I will, if the time lets me, I will end up with a question on GPS time as well. So let's get started. So we have divided time into pieces as long as history has been recorded, and the obvious divisions are years, months, and days, and I think this is the divisions we use are common across the world. More arbitrary division is the division of the day into smaller pieces. So the Egyptians already 4,000 years ago divided the day into 2 parts of 12. And they did it not in equal pieces, but they divided the day into 12 pieces, meaning that changing seasons meant that the part had different lengths. The Babylonians did basically the same thing, but they divided into pieces of 60s based on their numbering systems. Later, the Greeks, they also used the 60 parts and the 12 parts, but they divided the day into 24 equal length parts, so their hour were equally long throughout the year. In medieval Latins, then these subdivisions were called the pars minuta prima and the pars minuta secunda, which is where we have the names for the parts, the minute and the second. Time went on. There must have been different units to measure time, but the British Association for the Advancement of Science stated all men of science are agreed to use the second or mean solar time as the unit of time. So enough said, I mean, you can't argue with that. And then a few years later, there was an International Meridian Conference in Washington, D.C. that said that the Greenwich Meridian was the prime meridian, and obviously from there, the solar time had an origin. Later, when people started to use radio signals to synchronize clocks, they found out that the clocks differed more than you would expect. And so the Bureau International de l'Heure, BIH, was formed to get a system around this topic and to get a better synchronization of the clocks around the world. Roughly about the same time, people started to align the other units. And 150 years ago, the meter convention was signed. It was originally intended for the meter and the kilogram, but later also included the Kelvin, ampere, and volt. And it ended up in the 60s. So they tried to close the circle and include all units into the SI system. By this time, it had become quite obvious that the Earth rotation, which then set the definition for the second, was not constant. People want the units to be constant, and so they tried to find a constant definition. And they chose to define the second as the mean solar time in the year 1900. Now, this is a very precise definition, but it's also extremely impractical. I mean, what are you supposed to do with a definition that was valid 60 years ago? So at the same time, when this, the resolution at the General Conference of Weight and Measures was defining the second along these lines, it was the 9th resolution. The 10th resolution was to diligently try to find a way how to incorporate atomic time into a definition of the second. As the second last speaker pointed out, the cesium frequency standard was first demonstrated in 1955 by Perry and Essen, and then the BIH started to maintain atomic timescales already in 1960, and the atomic standard was accepted already in 1967, so only 12 years after the first demonstration of the cesium second. And this is an astonishingly fast time, which also proves how good it was and how bad the existing definition was. So more precise, it's around 9 gigahertz It's an electronic transition in the cesium atom. Also, new atomic timescales were defined. It's the Coordinated Universal Time in English, or the Temps Universel Coordonné in French. So it's CUT in English and TUC in French. So they chose the diplomatic solution UTC to name it. Also, the TAI was defined. And these were endorsed by the General Conference of Weight and Measures in 1955, and so gradually shifting out the GMT for universal time across the globe. The BIH was then defunct in '88, and the BIPM, the Bureau for Weight and Measures, took over the responsibility for keeping the coordinated timescales. I will just have a sip of water. So the current status is that the cesium transition is still the basis for the definition of the second. It has really served us well. It's 60 years old, almost. The UTC and the TAI is defined in what we call coordinate time. And this is a very fine distinction between the second and the UTC. So the second is the basis for the coordinated timescales. But the second is defined in proper time, meaning according to the theory of relativity, it is a second no matter where the clock is. Where the clock is, the second is as long as the clock says, if the clock shows a perfect second, according to the definition. However, if you have two identical clocks, and you keep one here, and you place one on the Himalayas, the one on Himalayas will drift off according to our clock. And it's a clear measurable difference. So the UTC and the TIA scales, they are defined on the geoid, that is the mean sea level on the Earth, co-rotating with the surface of the Earth. Must keep that in mind for the future. And these, the previous talker also mentioned that the BIPM, the Bureau International pour la Poids Mesure, they do algorithmic determination of the UTC. So the UTC is not a live timescale. The BIPM actually collects data for a month, and then they process the data, and a few weeks later they present the results. So you don't know what the time was in UTC until 1 month to 1.5 months later. We will come to this, why the UTC-SP is important. And what's being done is that you have timing laboratories across the world, RISE included. We report our atomic standards to the BIPM, and they weigh and average these clocks into what is called the échelle atomique libre, which is just an average. Many clocks, the more clocks you have, the more stable the average becomes. So we have approximately 500 clocks, we get something which is pretty stable. However, we don't know how this average lies according to the definition of the second. So that's why we have really, really accurate primary frequency standards. And there are only a few of these across the globes. We're talking like 5 to 10 units. And they are not operated continuously all the time. So it could be that there is only a few of these one being operated. And they're used to steer this échelle atomique libre. And then the result is the TAI. Now, people are quite conservative. So the UTC is actually steered to align with the solar time still. So we applied what is called leap seconds to keep the sun at noon at GMT within 1 second. And this is done by the IERS. So they make astronomical observations and the results are applied accordingly. If you want more information on clocks that are being reported or what the timescales looks like and everything, I recommend you to visit webtei.bipm.org. You find a lot of information there. And I will also spend some time on leap seconds. So they are applied to keep the UTC aligned with the solar time. They're applied according to a recommendation from the ITIU. There have been a decision by the General Conference of Weights and Measures to increase the tolerance by 2035. Because these leap seconds are really not popular. People don't like to use them. We want a continuous time scale, and I think the world is now mature enough to accept that time doesn't need to be bound by the sun in the sky. However, there is a risk of negative leap seconds before that, and this is something that has never happened before. You can see the dark curve, which you see in the background, is how the Earth solar time has changed with respect to the TEI over time, and the light green is the corrections of the UTC. Now this one is the derivative of the past slide. So this is the Earth rotation speed, length of day. And you have a slight increase over time. It's due to tidal friction between the Earth and the Moon. But on the short term, this is highly, highly random. So by chance, the Earth rotation has been positive, or the length of day has been positive, so the Earth has been a bit slower for the last years with respect to the definition in 1900. You remember, we fixed the second in the year 1900, which has then led for the need of injection of leap seconds. Now what has happened since this paper was published in 2015 is that the curve had continued downwards. So we have actually crossed the zero, and we are now sitting on it. And what will happen from here is highly random. No one knows. We could continue even further down, or we could go upwards really fast. So this will be continued. People have said that negative leap seconds just won't happen. They won't do it. But I don't think that we will break protocol. And it's no time to change the decision to increase the tolerance. So what will happen in the next years is quite interesting. But so far so good. So let's talk about time in Sweden. We are regulated by this regulation about Swedish Standard Time. It says that we are UTC +1. And if you remember what I told you, we don't know what UTC is until a month later. This doesn't help us very much if you want to do precise time measurement. But there is also a law for accreditation and technical control. And it states the importance of national laboratories. And it states that the national laboratory has the task, basically, to take care, or they're responsible for the measurements in the nation and their traceability to accepted standards and units. These national laboratories are appointed by the government. So we have a second regulation that states that the National Laboratory for Time and Frequency is RISE, Research Institutes of Sweden. And we are there are more national laboratories, but for time and frequency, RISE is responsible for time interval, point of time, and frequency. So basically, if you want to know what the clock is in Sweden, it's us you want to go to. And we do this, the previous presenter presented basically the same. He actually had a more detailed graph than I do. But in principle, we maintain a lot of clocks. We measure these clocks with respect to our timescale. We report it to the BIPM, and we also report the difference in our timescale to other timescales to the BIPM. And then, every month, we get the results back. We applied steering to our clocks, and we have connected them to offset generators, so we correct the clocks. So we get each clock that are connected to an offset generator gives us a time signal which is synchronized and synchronized to the UTC. And we have then 1 month of holdover. And you can see how this holdover works. We are the deep blue curve, and we also have the German national timescale, UTC PTB. We have the American UTC NIST, French Observatoire de Paris, and the USNO, which maintains the GPS satellite system. You see, we are fairly good, and this is basically as good. There are no national timescale that is better than any one of these. There are more that are on the same level, and there are a lot that are worse. We report 5 active hydrogen masers to BIPM and 6 cesium beam standards, or at least we did in January. And this then gives us approximately 5.5% weight of the shell atomic libre. And we have a linkage with the two-way satellite time and frequency transfer and GNSS. And this gives us a combined standard uncertainty of 1 nanosecond. So these points that we see in the graph, they have a 1 nanosecond uncertainty of where they are. We distribute time to Swedish society. We do it by network time protocol, NTS or NTS. We do it by position time protocol, White Rabbit, GNSS common view, and we also have this speaking clock, which you may know, Frökenur. Our best uncertainty is if you want to compare a remote clock to UTC SP, we can do it within 7 nanoseconds with 95% coverage probability. If you want to compare it to UTC, the best we can do is 10 nanoseconds, and that is of course because we don't know what UTC is, so we need to take some headroom for that. And the traceability scheme or the distribution is done like this. We can, if you are in demand of really high accuracy, we can distribute time directly to you, but if you're not in demand of that high accuracy, it's better if you use some other time service provider that can provide that service better, I would say. But then we provide traceability for that time service provider. Speaking of traceability, there are some more regulations. We have the MIFID state. I'm just giving examples here. So a high frequency trade should be within 100 microseconds from the UTC, and you must demonstrate traceability. The Agency for Civil Contingency, in their statutes, they say that all government agencies shall use correct and robust time traceable to use TCSP. And then there's the regulation of electronic communication that states that traceable time should be used in event logs. So traceability is a word that is frequently used. What is meant by traceability? So here, I think traceability is basically what they mean is you know where you get the time from, and you should know where that person get their time from, and all the way back to UTC. That is not, however, if you ask us what traceability is. So I will give you an explanation to what we mean by traceability. And we call it metrological traceability. And so there is a statement here. It's a joint statement from these 4 organizations, the BIPM, OIML, ILAC, and ISO. You may know some of them. And they say that metrological traceability is one of the elements that establish international confidence in the worldwide equivalence of measurements. So basically, if you have metrological traceability to the UTC, it is UTC. And it's the same UTC that someone else who has another traceability chain or metrological traceability chain has. But there is a caveat here. For this traceability to be valid, you need a measurement uncertainty. There is no way to compare measurement values if you do not have measurement uncertainty. And you get the measurement uncertainty by performing calibration. And they say here that for a calibration to be valid, it should be done either by a National Metrology Institute, it's us, or an accredited laboratory, someone else. So what does this mean in practice? So I have an example here with GPS time or GNSS time. So GNSS system time is not traceable or metrologically traceable in itself. It can be, by chance, it can be quite close to UTC, but it's not metrologically traceable. And you need two things basically for it to be metrologically traceable, because people use GNSS, we use GNSS, so it's a good mean, but the system time is not traceable by itself. So either, or not either, and you must connect the system time to something which is traceable. And that you can do by the common view measurement, basically to a UTC-K laboratory like us. So we look at the satellites, we determine how much do their clocks deviate from the UTC-SP, and then the user, they look at the satellites and they determine how much do their clocks deviate from the GNSS system time. And then we can take the difference and you know how much the user time deviates from a UTC-K scale, and then how much it deviates from UTC-SP. That's the first. And the second one is, in order to get, or this is basically a part, you also have delays. The system time is measured in the antenna, but that is not how you use the time. You don't use the time that you have in the antenna. You have a receiver and you have a delay in the antenna cable to the receiver. The receiver determines the time and then it distributes the time, or it compares the time which you have at another place. So you have a time reference point. And what you need to do is you need to calibrate the distance or difference in time from the antenna to the reference point. And that is the calibration. And it can be done by an accredited laboratory, or it can be done by us, then, a NMI. There is a good paper on this in Metrologia. I have a citation here. And also, just to mention about the use of system time. I attended a meeting where also a representative of the USNO, which then operates the GPS satellites. He attended. We talked about the traceability of GNSS time, and he took the word and he said, just so you know, for the record, we disencourage users to use GPS system time as their time base. And they do not want people to use GPS system time as their source of time. And my interpretation is, of course, the GPS is a military system. They want to be able to use it for their purposes. They do not want to take consideration people using their system for other purposes. Okay. Future time. This is my last slide. I will just give you a hint on what's on the horizon in the timing community. So, we have optical clocks. So for the last 10 years, the cesium standard has not been the most precise way to measure time. Actually, so-called optical clocks, which measure it measures other transitions in the atoms at much higher frequencies. So while the cesium definition is at 10 gigahertz or at 9 gigahertz, we now measure transitions which are in the terahertz level, or even above that. Doing so, we get much higher precision in our measurements. And also, just last year, we did nuclear clocks, not watching or measuring the electronic transitions, but actually measuring nuclear energy transitions, which are at even higher frequencies. So this has led to the debate about the redefinition of a second. And there are a few options on the table. It's being evaluated. There is a roadmap. It will probably be done in 34, perhaps, 30 or 34. And either another transition is chosen. So it will be just an update of the existing definition where you choose one atom and you choose one transition and you say that, okay, this is the frequency that we define. Or you choose an ensemble of transitions. So this will be more like a system or a method to determine the second. So you can have a weighted average of like 4 or 5 perhaps transitions, which have then different uncertainty levels, which could then be evolved over time. So if we manage to measure at even higher frequencies, we can plug them in, we can phase out some old transitions. And also we have the lunar timescale. As I told you, clocks at a different gravitational potential, they tick at a different pace. And so clocks in space and clocks on around the moon, which would then be used, for example, for a GNSS system on the moon. So they need to be very precise. And they will tick at a different rate than clocks on Earth. So one solution to that problem would be to have a separate timescale for the moon. And that's a work in progress. It's just a proposal, but it's a serious proposal. That's all for me. I would like to just mention that since the Meeting Convention is 150 years old, we are going to celebrate this in Borås. So you're all welcome to join. There will be a one-day event.
Appropriately enough, we do have a little bit of time. Is there any questions for Gustav?
Yes, Svante Nygren, Svenska Kraftnät. You mentioned the average sea level. How will the rise of the sea level affect time in coming years?
Yeah, I think it's. I'm not into the details of the algorithms, but I think that they actually compensate. So the geoid is recalculated, I think, continuously, and if it would change, then of course it would automatically affect the time scales. Yeah.
A question at the back, please.
Yes.
You mentioned redefining the second.
Yes.
Isn't that going to break the meter and all sorts of other interesting second order effects? Because the meter's defined based on the second.
Yes, of course. But the second has an uncertainty. So the definition is fixed. So the definition has no uncertainty. But the practical realization of the second has an uncertainty, and it's around somewhere in the -16, 10 to the -16 scale. But the optical clocks can be measured down to the -18 or -20 level. So what will happen is that it will be measured, and the transition frequencies that are chosen, or the frequency that is chosen, will be chosen such that it lies well within the uncertainty that we can now measure the second with. So it will not have any practical effect.
Okay, so you're not going to get any further or closer away?
No, definitely not. We will be a spot in the middle, to the best of our knowledge.
I would like to reply to Svante in the front there about sea level. When we have used GPS to measure, we can even measure the level which we are standing on here in Stockholm. And I can tell you that the Earth you are standing on is moving 5 centimeters up and down every 24 hours. So tonight, when you go home and you suddenly fall over, that is not because you have been drinking too much, that is because the Earth had moved up a little when you was walking. So you just know that.
Yeah, trivia, if you know the Lek Vänern, actually you think the sea level is flat, but because of the shift of the geoid, geometrically, one end is like 4 meters higher than the other end, geometrically, but you don't sense it because the gravity always pointing downwards.
Okay. So, if there are no more questions, then please join me thanking Gustav for a fantastic presentation. Thank you.
Thank you.